All right, welcome back. This is the Climate, Carbon, and Soil Health Room. Our next speaker is Dr. Rafiq Islam. He's an Ohio State University soil scientist. He's going to be talking selling soil carbon from no-till soils, adjust for decrease in bulk density. So Rafiq, thank you.
Thank you. Hey, I didn't choose this title. Randall asked me to make this title and talk that how people got confused that if I have no-till or organic amendments or other treatments, we can accumulate a lot of carbon and sell in the market, make a lot of monies. But in reality, it may not be that way because the calculation of carbon stock and the sequestration is pretty different because of bulk density. So that's what I'm going to show you some calculation and some example. So let's start. So we have the carbon, which we call Lord of the Rings, which regulates all these, even our life. When life formed, according to the Bible, 7 days, carbon was there to maintain the temperature. So life can develop. Otherwise, life would not develop. The temperature would have been almost 80 degrees, minus 80 degrees Fahrenheit. So think about carbon creates global warming at that time to create life, help to create life. So that's why I put that carbon is part of the life and the resources we have, soil, nutrient, water, air, all this mixed up with sunlight produces carbon or utilize carbon as food, feed, fiber, and fuel, all based on carbon. Life is based on carbon. So the ideal situation, what we had, the global warming or carbon cycle, is a balanced one. How carbon moves and carbon goes out is a balanced system. But because of our activities, we are producing too much, especially we, the human, because of industries, conventional agriculture, and other activities. So getting a little bit unbalanced. We have a lot of people. So few of the examples I'll show you. Conventional agriculture, we put a lot of carbon, nitrogen, phosphorus-based compounds, and we plow. We love to plow. When we don't have anything to do, we say, let's go and plow. So when all this goes, look at that, what we produce. A lot of greenhouse gases, carbon and nitrogen based, and a lot of leaching and runoff of phosphorus, carbon, and nitrogen. So as a result, we decrease our soil quality, decrease our nutrient use efficiency, but we increase crop yield because we apply a lot of fertilizer to degrade the baseline but increase the production. And there is another example that more you till, deeper you till, you are going to have more burning of organic matter from soil and produce carbon dioxide, which goes to the air, accumulate, and create problem. So this is Don Rikoski from USDA. He found that if we don't plow, we just produce only 10 gram per 10 square feet. I had to convert that. It was square meter. So for understanding easily, so I converted it into square feet. So only 10 gram. But if you plow more and deeper, 4 inches, around 50 gram. If you go 11 inches deep, you almost produce 230 gram of carbon per 10 square feet. So what we have to do? We reverse the situation, pulling carbon through our climate smart agriculture, sustainable agriculture, or regenerative agriculture, or what you call through no-till, cover crops, organic amendments, inorganic amendments, all kinds of system approach. So currently we have this much on the top, how much carbon we released, 5.5 billion tons of carbon emitted from fossil fuel industries and all these, 1.9 billion tons from land use, that is agriculture. And but what are the things we have, the accumulation? 1.7, let's start with 3.5 billion, which is atmospheric accumulation, what we have accumulated in the air. 2.2 billion, we have ocean uptake, and 1.7 billion, which is unidentified. So unidentified is nothing but soil carbon sequestration under no-till or climate smart agriculture or regenerative agriculture or the forest or the shrubs, especially boreal forest. Those are the unidentified carbon sink. So as I mentioned, that soil is one of them. So soil is one of them because a healthy and productive soil is a dynamic part of our ecosystem, which is biologically diverse, Warren and other speaker talked, and efficient under different system, chemically buffered. You cannot easily change the soil characteristics, so it's a buffered chemical reactions. Physically stable, that means if you keep the soil natural, it will be nice and good. Environmentally regenerative, it can regenerate by itself over time. Time is a big factor. Management responsive, that means whatever you do, it bounce back. If you do no-till, it may come positive way, or if you do plow again and again, it may go back. So look at that. So these are the characteristics. It makes the soil to sequester carbon or not to sequester carbon. So this is another Don Rikoski slide I've stolen. So his idea is climate smart agriculture, no-till or zero-till or direct seeding, no flow. That means we are not going to have any water erosion, no blow, no wind erosion, moving of soil, and no glow. That means plowing, putting oxygen, and burning the organic matter and produce carbon dioxide. So one of the example is conservation tillage using cover crops. So you undisturb and keep the residues on the soil, as Polyas has just said, and the cover crops just roll it over and plant within the cover crop. I just showed you one example, that's all. So when organic residues in any system goes into the soil, say 100 grams of organic residues goes into the soil, most of the carbon will decompose and it will last. Sorry. So 60 to 70 gram or percent will go out, only 3 to 8 gram or percent will stay in microbial cell. It's a range, and 3 to 8 gram or percentage will stay in humic, non-humic material, and 10 to 30 gram into humic material. Why is that variation? For example, tillage. If you have no till, you are going to be dominated by the system by fungus. And fungus, they like undisturbed condition, bigger residues, and decompose slowly. That's why the carbon use efficiency is 25 to 40%. But whereas in till system or plowing system, bacteria dominates. And bacteria, it eats everything. And it likes to survive. It's a well-adaptive survival organism, any disturbed condition. So their carbon use efficiency is 15 to 25%. So that's the tricky part of carbon sequestration, starts in the soil, biologically. Then we have chemical stabilization, physical stability. But that is the tricky part, how carbon accumulates in soil because of the small microbes. So in soil, the carbon accumulation capacity we have, so using the standard value of 1 milligram per carbon accumulation per unit of specific surface area. That means whatever surface area we have in sand, reactive surface area, silt and clay, which I have given Again, I had a hard time to convert everything from square centimeter per gram into inch. So look at that at 6 inches deep. Based on this concept, a loamy soil can sequester at 6 inches depth around 47 or 50 tons of carbon per hectare, maximum capacity, theoretical capacity. Silty clay loam around 80 tons per acre, and clay soil 150. So think about how much capacity of clay to absorb and sequester carbon. But carbon sequestration is not that easy. Carbon sequestration depends on labile, how labile it is. More labile carbon means more utilization by bacteria or fungus. So carbon will sequester, only the lability will go, drops down. So decreasing lability increases carbon sequestration. So that's another tricky part, and which depends on how much clay you have or how much disturbance you have. So this is our data, published data. So we had Warren's plot, Whiteville, Piketon, Alabama, Indiana, 4 different locations. And this is one study we did. We just published this on soil in Kazakhstan, one of the good soil, but disturbed soil. Again, it depends. Carbon accumulation depends on decreasing lability. That means carbon bound with calcium, iron, and other compound into little bit passive form. So that is the tricky part. Active carbon will accumulate. These are all based on active carbon, but active carbon is utilizing by organisms. So there is a balance. So theoretically, you can do a lot of carbon sequestration based on surface area, but in reality, you can't. Plus, we apply fertilizer, we apply amendments, pesticides. Some of those goes into the surface area to occupy. So if we want to accumulate carbon and sell in the market, what we have to do? We calculate how much carbon we have. So that is the main theme of the talk. So we have carbon stock, whatever unit we have is organic carbon percentage, bulk density, which is a very dynamic properties influenced by moisture, management system like tillage, cover crops, or amendments. And the depth, how much depth you want to go. And the factor, it depends on what unit you want. So based on that, we calculated one carbon sequestration at 2 different depths. Soils under barley with alfalfa of 0 to 4, 0 to 8, with alfalfa manure, alfalfa vermicompost. Look at that. The soil at 4 to 8 inches almost saturated with carbon. Why is that? Because of the lower depth. In the lower depth, why carbon is almost getting plateaued? Because it's the lowest, it's silt. It does not have that much surface area and reactivity. It's the lowest, like a silty material. That's why whatever carbon leached out from the top, it occupy all the spaces. On the top, it's still accumulating as particulate organic matter, free pieces, small pieces of organic matter. It stays on the top as particulate organic matter. That's what is accumulating on the top. And as I mentioned, bulk density. So if you look at the bulk density differences, how they affect growth of the plant, especially roots, and main thing, how much residue you have on the top of the soil is not that important. How much root you have, that is more important, because the atmosphere and the soil oxygen diffusion is very limited. Not that much oxygen goes into the soil. So no oxygen, no decomposition, less decomposition in the deeper layer. So if you have more root, you are going to have carbon accumulation as particulate organic matter bound within the aggregates because of lack of oxygen and disturbance, which is very much prevalent in no-till. But conventional till, you plow every year, you destroy them and expose them, all this carbon to the opportunistic bacteria, and which causes all the loss of carbon in the soil. So one example is, say, a farmer transitioned to his plowed field to no-till, and after 3 years, lab test shows his field contains 1.65% carbon with a bulk density of 1.5 gram per cubic centimeter at a depth of 12 inches. Initially, before that transition, the plowed soil had 1.5% organic carbon and bulk density 1.25. So if you compare this, use the calculation, traditional fixed depth, that we want to go 12 inches deep and calculate for both systems. So no-till, I calculated. Again, I had to use all this conversion into metric, into English system. 30 tons per acre, and plowed soil at the beginning of transition, 22.8. So the difference is 7, little more than 7. So carbon sequestration over 3-year period, 2.43 tons per acre, which is not possible per year. So that means something is wrong. That this much of carbon sequestration farmer wants, and say, oh, I have this much of carbon lab test set, so I want more credit, but actually this is not right. So look at here, what we have, fixed depth, no-till 12 inches deep and conventional 12 inches deep. But the bulk density is different. Bulk density is 1.5, which is very common in no-till at the beginning. After 1, 2, 3 years, bulk density goes up, then it drops down. So look at the difference. That means the mass of soil is different. So how much difference we have? Almost 20% soil more. We have no-till soil because of this high bulk density. And that counts into carbon stock. But when you want to sell carbon, nobody is going to buy your damn dirt. They say, oh no, it's a dirt. I don't want to buy this. So what do we have to use? We have to think about equivalent mass. That means apple to apple. Earlier we had apple to orange comparison. Now we have apple to apple comparison. We have to use equivalent soil mass. That means soil mass has to be same, and then make a calculation. So again, if you look at this calculation, so what it shows that if you take soil from no-till, transitional no-till, and conventional till, so conventional till, when you take 12 inches deep, it should be 10 inches deep in no-till soil. That way your amount of baseline soil is more or less same. Otherwise, you're going to have more soil. So look how depth it changes to make it more equilibrium. And now we calculate again. We found no-till soil stock, carbon stock, 25 tons, rather than so much earlier. And conventional till soil, same amount. The difference is 2.2 tons per acre. And carbon sequestration rate is 0.733 tons per acre. That means around 1,500 pounds. That is reasonable. So you can sell this much of carbon, not the one with 2.3 tons of carbon per year. No, that you cannot do that. And these are some of the examples I just showed how we calculated. Look at the column, first column treatment, different treatment depth in terms of time, 0 year, 3 years, 11 years, 18 years, 29 years, and the depth in terms of centimeter and inch. and organic carbon is very, very low because the lowest silty material doesn't hold that much. And then bulk density, we have that yellow. And based on this, we calculated the fixed depth soil organic carbon, this one, with fixed depth, F. And then when we adjusted the depth as per bulk density, this is the equivalent mass carbon stock. See the difference? And very, very low amount of carbon over the years. So using that information, we had a regression equation to see the fixed depth in the x-axis and equivalent mass of carbon stock on the y-axis. It shows that almost 0.1 ton per acre. That means 202 pounds of carbon was underestimated using the method of traditional same depth calculation. So that's what you'll find, that people are not going to buy. They say, no, you overestimated because you have soil. Those are not carbon. So this is just one example. And these are Warren's plot. Warren was managing those. We collected and we published the paper. Long-term no-till on bulk density at different soil depth. And look at that. So green one is 44, blue one is 23 years no-till, and pinkish is 2 years no-till, and conventional till is red. Look at that. 2 years no-till, bulk density increase because there is no disturbance, organic matter just coming in as residues. But over time, look at that, how bulk density has changed, decreased. So under this situation, when you are going to sell this carbon, it's complicated. And you think, oh, I have long-term no-till, I can get so much, which is true, but you have to be sure how do you do the calculation. So we did the same way with the regression and try to correlate. It shows that about 6.698 tons of carbon, that means around 1,400 pounds of carbon was overestimated by fixed depth sampling. So almost, more than half a ton of carbon we overestimated. So again, you cannot sell these. These are from the soil because of bulk density. David Brand farm. So two different depths, 0 to 6 and 6 to 12. Again, look at that. The x-axis is no-till and the y-axis bulk density. So initial transitional bulk density increase in both depths, but over time it decrease and stabilize. So you will see this situation when a farmer, when you go for certain, a transitional period. And based on this, again, the correlation, we found that around 0.15 tons, which is 302 pounds of carbon, underestimated this time, not overestimated, underestimated. Why is this underestimated? Because this line passed through this direction. So if it goes this direction, you are overestimated. So that slope tells us it's underestimation or overestimation. And this is the experiment we have at 4 different locations, 5 years experiment. Again, this is in Alabama. We have underestimated the carbon. So farmer is going to get less carbon, but actually he should get more carbon, more credit, carbon credit. This is in Whiteville. This is underestimated again. So farmer should get more money for carbon credit. This is in Indiana. Again, underestimated. If you use the fixed depth, the same depth for everything, you are not going to get exact carbon sequestration and So that's what you have to think about, that what I have to use. This is in Piketon, Ohio. Again, this is overestimated in this situation. And when we combine everything, all the soil, and it shows that it has slightly underestimation because we put all the mangoes, apple, orange together to see different state, sandy soil, clay loam, silty clay loam, clay soil, all kinds of soil in different sites. And this one is Newark mine reclaimed soil. We want to see if people planted forest, how they're going to get the carbon credit. So again, it shows that you have overestimation of carbon when you do this calculation. So certain situation, it's underestimation, certain situation, overestimation. So sandy soil, if you have more sand, you are going to get overestimation because sand has higher bulk density because of the bigger size. So the take-home message based on this, that soil carbon sequestration is heavily impacted by management practices, especially tillage. And tillage causes bulk density variation, which can distort the fixed depth sample, that means same depth sample, for calculating carbon stock by adding extra soil weight, which nobody will buy. Nobody wants soil. So equivalent soil mass approach can mitigate this issue, providing more accurate prediction of carbon sequestration, because it will compare same amount of soil, not the depth of the soil. It will take it out because of bulk density. So in the carbon market, which our good friend Mike Istad is going to take, how much money you are going to make. So the focus should be on selling carbon, not rather than not soil, to receive the credit in future. So this is one of our app which we are producing, Soil One, to calculate carbon sequestration calculator in future, so anybody can measure using the app. So that was the idea. So that's all I have. If you have any questions, I'll be glad to answer.